Hi everyone, today I'll be talking to you about a construction of PCPs that achieve a nearly optimal alphabet soundness trade-off, and this is joint work with Dor Minzer. To start, let's consider the 3-sat problem, which goes as follows. In this problem, you're given a Boolean formula as such. So it's a Boolean formula phi, and as you can see, it's an AND of clauses. Each clause is an OR of 3 literals, and we want to decide if phi is satisfiable or not. So the famous Cook-Levin theorem classifies the complexity of this problem, and it says that 3-sat is NP-hard. So this means that in some sense, 3-sat is really capturing the complexity of the class NP. And from reductions from 3-sat, we can actually show that many other problems of interest are NP-hard as well. So this theorem gives us a way to classify the complexity of many problems of interest in computer science. But what happens if we're interested in a different type of problem? For example, an approximation problem. For approximation, there's a similar another way to view 3-sat, and it's this optimization variant, which is called max 3-sat. In this problem, you're given a Boolean formula phi just as before, but now the goal is to satisfy as many of the clauses Ci as possible. So instead of deciding its satisfiability, we want to find out how many clauses we can satisfy at once. For the complexity of this problem, well, it's classified by the PCP theorem, and it says that max 3-sat is NP hard to approximate within a factor of 0.99. So this is a great fact in itself, and maybe a very surprising fact, but a lot of the efficacy of this PCP theorem isn't just in the statement that we have on the slide, but it's actually in its ability to show NP hardness of many other problems of interest via reductions. For reduction, it's often easier to work with the following form of the PCP theorem. And this form says that if you're given a 3-sat instance phi, then deciding whether phi is satisfiable or at most 0.99 satisfiable is NP hard. So it's not too hard to see that the previous form of the PCP theorem follows from this form, but this form will be much more useful for us when we start thinking about reductions. So how reductions from this problem we have often work? Well, they often use a sort of gadget that we'll call a two-prover one-round game. So in a two-prover one-round game, there's some 3-sat formula phi, and there's a verifier as well as two provers. And the two provers want to convince the verifier that phi is satisfiable. The verifier is not sure whether to trust them or not. So in order to check the satisfiability of this formula, they'll play the following game with the two provers. What they do is first choose a random clause Ci. Then from this clause, they'll choose a random variable appearing inside the clause. After that, they will send the clause to one prover, and then they'll send the variable to another prover. And they'll ask for assignments to each. So prover 1 will respond with a satisfying assignment to the clause Ci, while prover 2 will respond to an assignment to a single variable xj. Upon receiving the responses, the verifier will check if both provers gave the same assignment to xj, and they'll reject otherwise. So importantly, after this game starts, the provers are not allowed to agree on, are not allowed to communicate with each other. Beforehand, they can agree on a strategy of how they'll answer the questions, but after that, there's no more communication. And it turns out the PCP theorem is roughly saying the following. So it's essentially saying that if it gives us reduction from 3-sat, to two-prover one-round game, where if the original 3-sat instance is satisfiable, then the two-prover one-round game that we get has value 1. And here value refers to the maximum probability that the provers can win with. And for an unsatisfiable 3-sat instance, the PCP theorem is giving a reduction to a two-prover one-round game with value at most 0.99. So the provers can win with probability at most 0.99 in that no case. So to roughly see how this is shown, well, for a satisfiable 3-sat instance, the provers can certainly agree on some assignment beforehand, and they can always answer according to that assignment, and of course, they'll always win. For an unsatisfiable 3-sat instance, well, if we start from the second case of the PCP theorem, where phi is at most 0.99 satisfiable, then notice that 1% of the time the verifier is going to choose a clause that cannot be satisfied, and then in this case, the provers are going to have to resort to guessing. So here we have some constant gap between the yes and the no case, but we might want to amplify this gap. In particular, for certain applications in hardness of approximation, we'll want this gap to become an arbitrary large constant. So the gap is the 1 versus 0.99 in the yes and no cases. Kind of a natural way to amplify this gap, well, is to make the game harder for the provers to win. And we can make the game harder by asking more questions. So this is often called the parallel repetition, and it looks like this. So for the k-fold parallel repetition, the verifier is going to choose k random clauses, and then they'll choose one variable from each clause. Now to check the satisfiability, they'll send all of the clauses to one prover and send all the variables to the other prover, and now ask for assignments to all of those. So it stands to reason that if we make k very big, we're making it harder and harder for the provers to win in the no case. And indeed, this can be shown. So this is a result of Ross, and it shows that if we repeat this game k times, then in that no case, the provers are winning with probability at most roughly 0.99 to the power of k times some small but absolute constant. So now this is saying that if we want to get some arbitrarily large constant gap, well, we can obtain that by just setting k sufficiently large. So notice that as k gets larger and larger, this winning probability goes towards 0. Once again, this is wonderful. We can get any arbitrarily large gap we want. But notice that this gap amplification is coming at a cost, and that cost is to the answer size. So what I mean by answer size is the number of potential answers that the provers could give. In the original two-prover one-round game, you can check that answer size was 7, and that's because prover 1 is giving a satisfying assignment to a 3-sat clause. But once we do this k-fold repetition, parallel repetition, that answer size blows up from 7 to 7 to the k. So now let's just recap what the state of things is. So this answer size, formally, we'll call it the alphabet size from now on. And what we saw first was the PCP theorem, which states that distinguishing a two-prover one-round game of alphabet size 7 with value 1 versus value at most 0.99 is NP hard. We then saw that the gap between the yes and the no cases could be amplified. Formally, we saw that there's some constant greater than 0, such that for any k, a two-prover one-round game of alphabet size 7 to the k is NP hard to distinguish between the case where its value is 1 or its value is at most this m to this small negative constant power. So now let me mention that this value in the no case is often referred to as the soundness of the PCP. And what we're interested in is whether we can get alphabet soundness trade-off as efficient as possible. So note that we can make this soundness as small as possible, but in the process, we are making the alphabet size larger. So if we think about alphabet soundness trade-off and parameterize soundness in terms of alphabet, then what we have with parallel repetition is m to some small constant. But the best possible, if you think about it for a bit, 1 over m is a pretty natural lower bound. So this is just because the provers can always win the game with probability 1 over m if they just guess randomly. And now we have this gap, and we might want to ask, well, how much can this gap be closed? So I'll tell you now about some progress towards closing this gap. We saw already that we could get soundness m to the minus c for c, a small absolute constant. In 2011, the c was improved to nearly 1/6 by Cote and Safra. And in 2013, Chan obtained C nearly half. So we're getting closer and closer to this best possible soundness m to the minus 1. And in this work, we show that you can essentially obtain this, and we show that you can take C to be 1 minus little o of 1. Let me now mention that in the latter three results, this value in the yes case becomes at most 0.99 instead of 1. But for many hardness of approximation results, this difference doesn't really matter because what is actually important is the ratio between the yes and the no cases. So what we get is a nearly optimal alphabet soundness trade-off. Formally, our main theorem is the following. So we show that for any constant m, given a 2-prover 1-round game with alphabet size m, it's NP hard to distinguish whether its value is close to 1 or at most roughly m to the negative 1. So we've been talking a lot about this alphabet soundness trade-off and trying to really optimize it. And one reason for this, which was hinted at, is that better trade-off leads to better hardness of approximation results. So let's see some of these applications, and let's see this main theorem in action. The first application I'll talk about is to quadratic programming. So in this problem, you're given a matrix A with diagonal entries set to 0, and your goal is to find a -1, valued vector that maximizes this quadratic form. So on the algorithmic side, there's a log n approximation algorithm, and there's also a quasi-polynomial time reduction from 2-prover 1-round games. So if you use Cote and Safra as a result, you get quasi-NP hardness with a factor of roughly log n to the 6th. So unfortunately, Chan's result doesn't apply due to a large size blowup. However, we managed to avoid that, and if you plug in our improved result, then you get quasi-NP hardness to approximate within a factor of nearly log n. So note here that our hardness factor is almost matching the best known algorithm. The next application is to bounded degree CSPs, and this is the following problem. Given a graph with maximum degree D, an alphabet for each vertex, and some constraint, you want to find an assignment that satisfies the maximum number of constraints. So these constraints specify what is a valid labeling along each edge. So there is a simple D plus 1 over 2 approximation algorithm that uses dynamic programming, as well as a randomized reduction from 2-prover 1-round games. So if you apply Chan's result, then you get hardness with a factor of nearly d over 3. Lee and Monarangzi showed that if you assume what's something called the unique games conjecture, then you can improve this factor to roughly d over 2. But we showed that, in fact, you don't need that assumption, and we get hardness of roughly d over 2 using our improved PCP. The final application will be to rooted K connectivity. So in this problem, there's a graph G, and each edge is given a cost. And then there's a root vertex, a set of terminals, and some connectivity requirement K. The problem is to find a minimum cost subgraph with K vertex disjoint paths from the root to each terminal. On the algorithmic side, there's a K log K approximation algorithm. And there's also a randomized reduction from 2 per 1 round games. So if you use Chan's result, you get hardness within a factor of roughly K to the 1/10. And if you use our improved result, then this improves to nearly K to the 1/5. So those are 3 applications of our main result. And for the remainder of the talk, I'd like to tell you a little bit about how our PCP is constructed. So after many reductions, what we really end up analyzing is some low degree test. So this test works as follows. We're given 2 tables. The first is T1, and it assigns every R-dimensional subspace in a finite field vector space a linear function. So for inside of a finite field vector space, we assign every R-dimensional subspace U this linear function over U. T2 is the same thing, but for 0.99 times R dimensional subspaces. And the low degree test we analyze proceeds as follows. So you choose a big subspace U, a smaller subspace V, and you check that the 2 tables agree. The point is that T1 and T2 should be obtained from some global linear function. And if that's the case, then you can see that this test always passes. We're interested in what happens when this test passes with some non-trivial probability. And this later it leads us to considering the following sort of combinatorial subproblem. So once again, I'm skipping a lot of steps and fast forwarding, but this combinatorial problem I'm about to tell you about is really where most of our effort lies. And the setup is the following. So suppose there are a very large number of hyperplanes Wi, and associated with each hyperplane is a linear function Fi. And these pairs Fi, Wi are epsilon good, meaning that Fi agrees with the table T1 on an epsilon fraction of entries contained inside of Wi. So you should think of this as there being many functions that have local agreement in the table. Local meaning that this agreement is within a hyperplane Wi. Now, what we really want in the PCP is global agreement. And what we want to say is that if this scenario happens, there is actually global agreement. So that's what we end up showing. So we show that if you assume the first 2 bullets, then you can actually construct this global linear function f star. So now f star is on the entire space, and f star has non-trivial agreement with the entire table. So before we had this epsilon local agreement, now we construct f star, and it has epsilon over 5 global agreement. And this is really a key step of our paper. Let me tell you a little bit about what goes into the proof. So first, just to restate what we show that if you have a lot of functions that have epsilon local agreement, then you actually can find a function that has epsilon over 5 global agreement. Firstly, I should mention that a similar statement is shown in the 2 to 2 games theorem, except there the agreement goes from epsilon to the 12th. Now the exact same thing would have applies to our case, but this epsilon to the epsilon 12 loss is too much for us. And we really need to tighten that up. And the reason that we can't afford this loss is because we're setting epsilon almost equal to q to the minus r. And q to the minus r is sort of this like trivial agreement threshold. So if you if you end up having agreement less than q to the negative r, then it's not really meaningful because that level of agreement with the table is trivial. So in fact, since we set epsilon so close to q to the minus r, we can't even really afford this polynomial loss. We really have to go from epsilon to the epsilon over 5. Even epsilon to the 1.1 would be too much for us. So the proof uses a lot of techniques from previous low degree testing literature. So it uses this transitive consistency graph technique from Raz and Safra. This is from their original plane versus point analysis. It also uses this boosting technique from much more recent low degree testing works. We also use some facts about this sunflower-like arrangement of subspaces. And finally, we use global hypercontractivity on the Grassmann graph. So again, showing this lemma on the slide is really where a lot of the effort of our paper goes. After we show this result, we're able to construct the PCP. So yeah, thank you for listening, and I hope you enjoyed.